Welcome back to JVM Internals Crashcasts. I'm Sheila, and with me, as always, is our JVM expert, Victor. Today we're diving into a crucial topic for any Java developer, common performance pitfalls. But before we get started, let's test your knowledge with a quick quiz question. What's the most common cause of memory leaks in Java applications?
That's an excellent question, Sheila. It's definitely going to make our listeners think. Memory leaks can be tricky to spot and fix, so I'm curious to see what our audience comes up with. Let's break it down a bit. In Java, memory leaks are different from those in languages like C or C++. Here, it's more about objects that are no longer needed but still hanging around in memory. Think about long-lived objects and how they might be keeping unnecessary connections to other objects.
Great point, Victor. Now, let's set the stage for today's discussion. We're currently in the performance tuning chapter of our Level 3 JVM Expert season. We've covered JVM flags and tuning options, as well as profiling and monitoring tools. Today, we're focusing on common performance pitfalls. Victor, could you start by giving us an overview of what we mean by performance pitfalls in the context of Java and the JVM?
Certainly, Sheila. Performance pitfalls are basically common mistakes or oversights that can lead to slower or less efficient Java applications. These can range from simple coding errors to more complex issues related to how the JVM manages memory and runs code. Some examples include memory leaks, creating too many objects, using inefficient algorithms, and misusing synchronization. These pitfalls can cause slower execution, higher memory usage, and in some cases even crash the application.
That's a great overview, Victor. Let's start with something that many developers struggle with: memory leaks. I understand that in Java, the garbage collector is supposed to handle memory management for us. So, how do memory leaks even happen in Java?
You're right, Sheila. The garbage collector does handle most memory management, but it's not perfect. In Java, memory leaks typically occur when objects are no longer needed, but are still being referenced somewhere in the code. This stops the garbage collector from removing these objects. A common example is using a static collection to store objects. If you keep adding to this collection without ever removing items, it will grow indefinitely, causing a memory leak.
That makes sense. So, it's not really a leak in the traditional sense, but more like objects overstaying their welcome in memory. What are some best practices to avoid these types of memory leaks?
Great analogy, Sheila. To avoid these issues, developers should be mindful of object life cycles, especially when dealing with long-lived objects or caches. Some best practices include 1. Using weak references or soft references for caching scenarios. 2. Implementing proper cleanup methods for classes that manage their own resources. 3. Being cautious with static fields, especially collections. And 4. Regularly reviewing and cleaning up any manually managed caches.
Those are helpful tips, Victor. Moving on to another common pitfall: excessive object creation. I've heard that creating too many objects can be a performance problem, but isn't object creation in Java supposed to be relatively cheap?
That's a common misconception, Sheila. While Java does optimize object creation, making too many short-lived objects can still slow things down. This is especially true in tight loops or high-traffic scenarios. The issue isn't just the creation cost, but also the extra work for the garbage collector. When we create many objects quickly, we force the GC to work harder and more often, which can cause noticeable pauses in how responsive our application is.
I see. So how can developers strike a balance between the convenience of creating objects and maintaining good performance?
Great question. There are several strategies. 1. Object pooling for expensive-to-create objects. 2. Using primitive types instead of wrapper classes when possible. 3. Employing the flyweight pattern for sharing common object states. 4. Utilizing string builder for string concatenation in loops. And 5. Considering value types coming in future Java versions for small, immutable objects. Remember, it's about finding the right balance. Optimizing too early can lead to more complex, harder-to-maintain code. Always profile your application to identify real bottlenecks before optimizing.
That's really helpful, Victor. Now, let's talk about a more algorithmic issue: inefficient algorithms. Can you give an example of how choosing the wrong algorithm can impact performance, even if the code itself looks clean and well written?
Absolutely, Sheila. A classic example is choosing the wrong data structure or algorithm for a specific task. Let's say you're implementing a search function for a large dataset. If you use a simple array list and perform a linear search every time, your application might work fine for small datasets. However, as the data grows, the search time will increase linearly, potentially causing significant slowdowns. In contrast, using a hash map for lookups or implementing a more efficient search algorithm like binary search for sorted data could dramatically improve performance.
That makes a lot of sense. It seems like understanding the characteristics of different data structures and algorithms is crucial for writing performant Java applications. Are there any tools or techniques that can help developers identify these algorithmic inefficiencies?
Absolutely. Profiling tools are invaluable for identifying performance bottlenecks, including algorithmic inefficiencies. Tools like JProfiler, YourKit, or the built-in Java Flight Recorder can help you pinpoint methods that are taking too long to execute. Additionally, Big O notation is a crucial concept for developers to understand, as it helps in evaluating the efficiency of algorithms theoretically. For practical performance testing, using JMH, Java Micro Benchmark Harness, can provide insights into the actual performance of different implementations.
Those are great resources, Victor. Now, let's switch gears a bit and talk about synchronization. I know that proper synchronization is crucial for thread safety, but I've also heard it can be a source of performance issues. Can you elaborate on this?
You're right on both counts, Sheila. Synchronization is indeed crucial for thread safety, but improper use can lead to significant performance problems. The main issues are: 1. Overuse of synchronization. Locking more code than necessary can create bottlenecks, as only one thread can execute a synchronized block at a time. 2. Using synchronized collections when not needed. For example, using vector instead of array list in a single threaded context. And 3. Lock contention. When multiple threads frequently compete for the same lock, it can lead to threads waiting and context switching, which hurts performance. To mitigate these issues, developers should aim to synchronize only what's necessary, consider using more fine-grained locking, and explore lock-free data structures where appropriate.
That's really insightful, Victor. It seems like there's a delicate balance between ensuring thread safety and maintaining good performance. Are there any modern Java features that can help developers achieve this balance more easily?
Absolutely, Sheila. Java has introduced several features to help with this. First, the java.util.concurrent package provides high-performance, thread-safe collections, like concurrent hash map. Second, we have atomic classes, like atomic integer or atomic reference for lock-free thread-safe operations. Third, the lock interface and its implementations offer more flexible locking than synchronized blocks. And fourth, completable future helps compose asynchronous operations without explicit synchronization. These features allow for more fine-grained concurrency control and can often provide better performance than traditional synchronization techniques.
That's fantastic, Victor. As we're nearing the end of our episode, could you summarize the key takeaways for our listeners about avoiding common performance pitfalls?
Certainly, Sheila. Here are the key points to remember. 1. Be mindful of object life cycles to prevent memory leaks. 2. Avoid excessive object creation, especially in performance-critical sections. 3. Choose appropriate data structures and algorithms for your specific use case. 4. Use synchronization judiciously and leverage modern concurrency utilities. 5. Always measure and profile before optimizing. Premature optimization can lead to unnecessary complexity. And 6. Stay updated with Java's evolving features that can help improve performance. Remember, performance tuning is often about finding the right balance between clean, maintainable code and optimal performance.
Excellent summary, Victor. Now, let's reveal the answer to our quiz question. What's the most common cause of memory leaks in Java applications?
The most common cause of memory leaks in Java is often static references to objects, particularly in collections. When objects are stored in static fields or collections and not properly removed when no longer needed, they persist in memory for the lifetime of the application, leading to memory leaks.
Thank you, Victor, for all these insights. In our next episode, we'll be moving on to a new chapter about JVM languages, where we'll explore how languages like Kotlin, Scala, and Clojure work on the JVM. Until then, listeners, keep experimenting with these performance optimization techniques and don't forget to profile your applications. If you enjoyed this episode, please subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue producing this content. See you next time.